previous lectures we have discussed two specific techniques, chromatographic techniques, one ion exchange chromatography and gel filtration chromatography. One was based on the charge an analyte carries and another was based on the size or shape of the molecule. Today we are going to discuss about another chromatographic technique, which is affinity chromatography, which has very high selectivity. Now, lot of molecules or substances, they interact with each other quite strongly, and this is the basis of affinity chromatography. That is, one molecule has high affinity for another molecule and will bind to it reversibly, but strongly. So, affinity chromatography separates proteins or other analytes on the basis of a reversible interaction between a protein or say group of proteins and a specific ligand coupled to chromatographic matrix. Now, this combinations, there could be lot of different kinds of combinations, like say protein inhibitor combination, it could be receptor hormone combination, it could be avidin biotin combination, or it could be simply antibody antigen combination. Now, this technique is ideal for a capture or intermediate step in a purification protocol and can be used whenever a suitable ligand is available for the protein of interest to be purified. With a very high selectivity and hence high resolution, high capacity for the proteins of interest could be obtained. So, purification levels in the order of several thousand fold with high recovery of active material are achievable in this technique. Target protein can be collected and purified and also could be concentrated. Mostly it is like in a concentrated form as in ion exchange chromatography, but it is much more selective than ion exchange chromatography. So, it is a high capacity with high selectivity and with high and have much higher resolution. Now, biological interactions between ligand and target molecule can be a result of electrostatic or hydrophobic interactions. It could be van der Waals forces or hydrogen bonding. Now, to elute the target molecule from the affinity medium, the interaction can be reversed either specifically using a competitive ligand or non-specifically by changing the pH or ionic strength or polarity. So, if I have to explain in a very simple way, let me explain this technique on your screen. Now, so what is happening is, first thing is that you have to choose a pair, that is the ligand which needs to be immobilized for a particular protein of interest to be purified, and this ligand then needs to be put on the matrix, that is support material. So, what you have is, supposing this is your support material, and which could be anything like, as we will discuss, agarose or dextran or polyacrylamide, depending on what you choose to use. There will be a particular ligand which will be immobilized. Say this is your ligand which is immobilized, this is your ligand. Now, this ligand could be immobilized either directly onto the matrix or it could be immobilized through a say spacer arm, which spacer arm could be 6 to 8 carbons or others, as we will discuss, and then it could be the ligand could be attached to the spacer arm. A spacer arm is attached to the matrix. Now, this kind of increases the accessibility of the protein to be purified to the ligand. Sometimes if the larger molecules or bigger molecules, if the ligand is too close to the matrix and because of matrix physical like conformations, protein cannot access. So, in any ways, in either case, what is happening is there is a protein or this is an analyte which has a complementary shape here. All right, this is just an schematic to make you understand. Now, when the protein molecule to be purified is loaded onto the column and this ligand which is immobilized, like charges are immobilized on a stationary phase. This ligand is also immobilized, and one bead might carry many ligands, and also the porosity and other factors will certainly affect the flow and binding. So, as this protein molecule or many of the protein molecule will come, they will be binding to this particular ligand, and due to their biological interactions they will bind. Now, here affinity has to be good enough in a sense that it binds specifically, and non-specific binding could be avoided, and it should be reversible also, so that you can elute the sample. So, once it is bound, then second step would be to wash the contaminants and then elute this protein. Now, elution could be done by either I can take a free ligand here in higher concentration. Now, when you have a free ligand in higher concentration, what will happen? This free ligand in higher concentration will replace the bound ligand to the column. So, what you will get in, you will get a elution pattern where the free ligand has replaced the bound ligand, and this whole thing could be then passed in the elution or as a eluate from the column. So, this is how you will be able to purify the sample very specifically, and it is a high capacity and high selective. Now, you can also elute it by changing the pH and other conditions. So, this is in a very simple way, this is the basis of affinity chromatography. All right, let us explain this, let us get into the details of this technique. Now, here if you see what I have explained, this depicts the same thing. You have a ligand which is a spacer arm, this comes and binds here, then this could be eluted with another free ligand, or pH conditions could be taken, and then you can restore and then again purified enzyme is obtained, and this could be used as many times as you want by cleaning it up. All right, let us discuss different things about this chromatographic techniques. There are certain terms which are important. One is matrix, which we have discussed earlier, but in terms of affinity chromatography. So, matrix for ligand attachment is very important. So, matrix should be chemically and physically inert and should be able to attach to the ligand. Then spacer arm like I have shown you, it is used to improve the binding between ligand and target molecule by overcoming any effects of the steric hindrances of the matrix. Ligand is a molecule that binds reversibly to a specific target molecule or group of target molecules. Then binding, the buffer conditions are optimized to ensure that the target molecule interact effectively with the ligand and are retained by the affinity medium, as all other molecules will be washed through the column. So, the binding is another important term here. Then elution. In elution, in affinity chromatography, buffer conditions are changed to reverse the interaction, that is weaken the interaction between the target molecule and the ligand, and like I said, it could be done specifically or non-specifically. Then you wash for the column for non-specific bindings, so that unbound substances which are not really needs to be binding there will be taken off. Ligand coupling is another important term. It is a covalent attachment of ligand to a suitable pre-activated matrix to create an affinity medium. So, this could be done commercially, these resins are available, and even this could be done like you can purchase a pre-activated matrix and you can couple a particular ligand. Pre-activated matrix, like I said, it is a matrix which have been chemically modified to facilitate the coupling of the specific type of ligand, and you can purchase it and could be attach any particular kind of ligand. Now, the operation of affinity chromatography involves a lot of different steps. If you go through if you have to do affinity chromatography, then you have to go through certain steps. One is you have to choose an appropriate ligand. So, you have to know what you are going to purify or which group of analytes or proteins you are going to purify. So, the choice of an appropriate ligand is the most important. Then immobilization of the ligand onto a support matrix, so that you can really do that particular purify the particular analyte. Then contacting the protein mixture of interest with the matrix, that is the another important part. Then removal of non-specifically bound proteins, and finally elution of protein of interest in a purified form. If I see this particular figure, if you can see here, this is very simple. Like what you have done is, first thing is you have a ligand, this is kind of immobilized, and you have to equilibrate in a particular buffer. These protein molecules are coming and binding in here, as you can see, non-specific binders will not be allowed. Then what is done? You will be eluted by target protein will be eluted or recovered by changing the conditions, and finally you can regenerate it. Now you can see here this graph, this is for non-bound compounds or non-specific, these are comes out, and then your peak could be eluted as a very sharp peak in a concentrated form. So, if you consider design and preparation of affinity chromatography matrix, there are like I said, it requires choosing certain particular things in affinity adsorbent for a purification of a particular protein, and it involves three major steps or three major factors here. One is choice of suitable ligand, selection of a support matrix and spacer, and then attachment of the ligand to spacer matrix. So, let us discuss each of these things here in detail. Now, first thing is choice of suitable ligand. So, what kind of ligand one needs to choose for a successful affinity purification? Now, so this requires, for a successful affinity purification, you require a biospecific ligand, that is that particular ligand could be covalently attached to a chromatography matrix, and it should be attached in a way that it does not lose its binding capacity. So, the coupled ligand must retain its specific binding affinity for the target molecule, and after washing away unbound material, the binding between the ligand and target molecule must be reversible. So, reversibility is a very important factor, otherwise you will not be able to elute the sample and purify the sample in active form. Any component can be used as a ligand to purify its respective binding partner. There are a lot of different biological interactions, and there are typical biological interactions used in affinity chromatography. For example, there could be say enzyme substrate interaction, or substrate analog could be taken. There could be antibody antigen interaction, there could be lactin polysaccharide interactions, nucleic acid and like say enzymes interaction, hormone receptor interaction. So, there are a whole lot of interactions which are in present here, like I said avidin biotin could be there, lot of interactions could be there, and these are natural biological interactions which are occurring all the time and could be utilized for affinity chromatography. Now, the factors to consider when selecting a ligand for protein purification are like specificity one. Now, specificity is very important. The ligand should recognize only the protein to be purified, it should be highly specific. Now, there could be two different types of ligands. One is monospecific, that is they will recognize only one type of substances or compounds or proteins, we can say these are called monospecific compounds, like for example, monospecific antibody. There could be that a possibility that ligand is known to recognize a group of compounds or group of proteins, then it will be called group specific in nature. Some typical examples of ligands suitable for the purification of proteins by affinity chromatography are, as you can see on your screen, like protein A or protein G, which could be utilized for immunoglobulins, monoclonal antibodies for different kinds of antigens, then nucleotides for nucleic acid binding proteins, lactins for glycoproteins, sugars for lectin and glycosidase, and likewise you can use lot of different combinations. So, one was specificity, which is very important. Then second is reversibility, that is very important, that ligand should form a reversible complex with the protein to be purified. So, the complex should be resistant to the composition of the feed stream and washing buffers, and the complex should be easily dissociable without requiring denaturing conditions. So, it should be affinity should be high enough, but not so that it becomes irreversible. Then stability of the ligand is very important. It should be stable to the conditions to be used for immobilization, as well as the conditions for elution and other things, like say resistance to proteolysis, resistance to denaturation by eluents or cleaning agents. That is very important for a ligand to be immobilized. Now, the size of the ligand, if we consider, then ligand should be large enough such that it contains several groups to interact with the protein, resulting in sufficient stereoselectivity and affinity. Then ligand should contain a functional group which can be used for immobilization without affecting the protein binding characteristics. Remember, if it is connected in a way that its binding site is kind of inhibited, or it is towards the matrix, then it is of no use actually. So, it should have a functional group which can bind to the matrix without affecting its binding characteristics. A smaller ligand may not be accessible to protein molecules because of the matrix backbone interference. So, many times spacer arms could be utilized. Very large ligand is likely to be more susceptible to denaturation and degradation. So, it can also cause increased non-specific binding through other parts of molecules. So, these things needs to be taken care when you are choosing the size of the ligand. Now, affinity, like I said, the interaction of a protein which is say P and ligand L can be described in this, that is P plus L equilibrates with P L, and the dissociation constant could be given by this equation here. If you consider that a substance which is have a substantial absorption of the protein from solution, it should have like values of the dissociation constant must be about 2 orders of magnitude less than the concentration of immobilized ligand. Now, many affinity techniques they operate quite well between the dissociation constant of 10 raised to power minus 4 to 10 raised to power minus 8 molar. So, that is how you can select a particular ligand. So, this was about ligand. The next important thing is support matrix and the spacer. Now, when you are selecting the matrix, there are few things needs to be taken care of. A ligand is immobilized to a solid support or matrix via one or more covalent bonds. So, the effectiveness of the immobilized ligand in purification will depend on the structure of the matrix, and following criteria as we are going to discuss are very important in selection of the matrix. One is that matrix should have a high degree of porosity, so that right flow rates and the protein's accessibility could be achieved. Large proteins like we have earlier also discussed will have problems if there is not enough porosity, and they needs to have unhindered access to the ligand immobilized on the interior portion of the lattice. So, that is another important part where cross linking is taking place. Then high porosity is a very important factor. Then the matrix should be chemically stable under the conditions used for activation and coupling, as well as they are used during operation and regeneration. So, those conditions there will be lot of different conditions and matrix needs to be stable. Then matrix should be physically rigid in order to allow good flow properties. This is very important for any chromatography, that mechanical properties of matrix where it should be quite rigid, so that right flow could be obtained, or you can say even flow throughout the running could be obtained. Then matrix should withstand a reasonable range of pH and temperature change. Matrix should be easily activated for coupling in case of affinity chromatography. coupling of ligands at high density and should be inert to non-specific binding of proteins. Matrix properties should be substantially altered on functionalization. So, if matrix is there, it should not be substantially altered when you are doing all this processing, chemical processing with this matrix. Matrix should be uniform in structure, particularly when functionalized, so that ligand molecules can be homogeneously distributed. That is very important. Now, there are a lot of different kinds of matrices are used. Commonly used matrices include agarose, dextran, then polymethacrylate, polyacrylamide, cellulose, controlled pore glass could be utilized, silica and so on. So, there are a whole lot of different matrices are available. Now, once this matrix is chosen, it has to be pre-activated and then ligand has to be put in. Now, many times you one needs to put spacer arm. So, when you have to choose a spacer arm for connecting ligand and matrix, there are certain things to be like if you see in general, spacer molecule is used to distance the ligand from the matrix. And so, when a small size of the ligand excludes it from free access to protein molecule in the solvent, ligand is immobilized through near enough to the protein binding surface to interfere with the protein binding. So, what is happening here is because of say ligand is smaller and it is very close to the matrix, the protein which is larger to be purified is not able to access the ligand, and in that case you need to include a spacer arm. Now, length of the spacer is very crucial and must be determined very carefully, and the number of methylene groups most often successfully has been used is from 6 to 10. So, the chemical nature of spacer is critical to the success of separation. Now, some spacers or spacer arms are hydrophobic, but most commonly consisting of methylene groups, but there could be others which are hydrophilic in nature and may contain carbonyl or amido groups. Now, spacers should be resistant to bind protein, that is non-specific binding should not occur, and it should be stable chemically, like for example, it could have a chemical nature, say hydrophobicity or hydrophilicity or charge. So, it should be resistant to bind protein itself, like non-specific binding should not occur. There are a lot of different examples of spacer arms. They could be like 1,6-diaminohexane is used, 6-aminohexanic acid is used, 3-aminopropyl, succinylated aminopropyl and so on. There is a list of spacer arms is available. Now, attachment of the ligand to a spacer matrix when it is needs to be done, then large number of methods have been developed for coupling ligands to matrix material. The most common procedure is to link a coupling agent to the matrix material and then add the ligand. So, what we see is pre-activation of the matrix. So, the reaction conditions and the relative proportion of the reagents will determine the number of ligand molecules that can be attached to each matrix particle. Now, there are certain coupling agents which are available which will activate the matrix, so that the ligand could be put in, like say cyanogen bromide activated agarose. Cyanogen bromide is a very commonly used coupling agent. It reacts strongly with amino group. It is extremely useful in coupling enzymes, coenzymes, inhibitors, antigens, antibodies and so on. There could be others like 6-aminohexanic acid and 1,6-diaminohexanic agarose could be utilized in case of small ligands where steric interference occurs because ligand is too near to the matrix surface. It is a 6 carbon atom spacer is inserted between the matrix and the ligand here by using agarose, to which 6-aminohexanic acid or 1,6-diaminohexane are coupled. So, you can have a coupling agent with a spacer arm. This could be utilized in this case. Then there could be a lot of others like epoxy activated agarose, and it is the agarose to which 1,4-bis 2,3 epoxy propoxy butane is coupled, which contains free oxirane groups. This group allows linkage of sugars, carbohydrates, or any other ligand containing a hydroxyl amino or thiol groups. And then there could be thiopropyl agarose, and there are other materials which are available in here. There could be carbol diimidazole activated agarose could be utilized in place of CNBr coupling, and this is like utilized that like many times the CNBr coupling or cyanogen bromide coupling, the N nucleophile reacts with the cyanate ester of CNBr, resulting in an isourea linkage, and that carries a potential charge and can act as an ion exchanger, and thus affinity chromatography will be kind of specificity is decreased. So, the chromatography run might not be proper. So, to avoid this problem, carbonyl diimidazole could be utilized rather than the CNBr. Then there are aminoethyl or hydrogide activated polyacrylamides which could be utilized for coupling, and lot of alternative coupling procedures are available which could be utilized here. If you see here on your screen, there is a very simple way of showing activation and coupling. So, first thing is activation and then couple the ligand. So, if you can see in case of say cyanogen bromide, it acts and it is activated in here, and then to this group it is very easy to couple the ligand in here through CN group. Likewise, there are other examples here which could be there are other functional groups, and they could be activated, and finally, the ligand could be immobilized. So, these are methods which could be utilized for immobilization of different ligands through activation and coupling. So, a lot of chemistry is involved here, which we have not gone in too much of detail, but that is important. This chemistry can be done in your lab also, but many times you might not be able to do it very uniformly when you repeat it, or many ligands may not be attached because of certain problems unless you do it very carefully. Otherwise, commercially available matrices with coupled ligands could be always purchased. So, they are always already activated and coupled. You have pre-activated matrices that could be utilized if you have to couple a particular ligand. Now, estimation of ligand concentration can be done. It is very essential to determine the success of a ligand immobilization. When you have done this, like I said, it is sometimes not so successful in lab conditions, but you have to determine the success of ligand immobilization, and it could be done by different methods like difference analysis. So, what you can do is by measuring the amount of ligand added to the coupling mixture, and that could be recovered after washing procedures. So, difference analysis could be one method. There could be direct measurements where absorbance of derivatized and underivatized matrix can be compared, and derivatized gels can be assayed for protein using Lowry method. Direct element analysis can be done if the immobilized ligand is having a unique group, say for example, phosphate, there could be direct analysis. This could also be done by a radioactive ligand. Now, if the radioactive ligand is incorporated into the coupling reaction, then it could be analyzed for total immobilized ligand. So, there could be different methods of to analyze the ligand binding in here. So, affinity chromatography, like I said, very highly selective, high capacity, gives high resolution, and it could be utilized for separation of many different kinds of analyte. There are a lot of different kinds of chromatography techniques which are available in affinity chromatography, like different combinations and different types of like basic we have discussed here, but let us see what are different combinations or different types of affinity chromatography. So, here the ligands that are used in affinity chromatography are either we said group specific or monospecific. On the basis of these ligands, a lot of different combinations of affinity chromatography could be there, and for example, lectin affinity chromatography. Now, lectins are a group of proteins produced by animals and plants and other organisms, and they have the ability to bind carbohydrates specifically and hence glycoproteins. So, they have a polymeric structure, most being tetrameric, and their subunits may be either identical, in which case they recognize a single specific saccharide, or of two types, in which they can recognize two different saccharide molecules. They are highly valuable in the purification of glycoproteins, particularly membrane receptor proteins, and once the glycoprotein have been bound to the immobilized lectin, elution can be achieved in a number of different ways, we have discussed earlier, like for example, by affinity elution using simple monosaccharide for which the lectin has the affinity. So, you can have a free monosaccharide which can be used through competition. By use of borate buffer, which forms a complex with glycoproteins, it could be utilized for elution. You can change pH, that could be one method for elution, or by addition of a reagent like such as ethylene glycol to reduce ligand hydrophobic interactions. Lectin affinity chromatography can be carried out in the presence of relatively high salt concentration, because it does not rely on ionic interactions, and it is also used to separate mixtures of cells by taking advantage of the saccharide component on outer membranes. So, if you see here, this is a very simple depiction that you have two kinds of one is glycoproteins, another are simple proteins. This is lectin, and so glycoproteins will bind, others will not bind in the mixture, and then you can elute it by having the monosaccharide, or different methods you can use for elution. So, this is a very simple depiction of this particular chromatography technique. Then there could be immunoaffinity chromatography. Immunoaffinity, when we say, necessarily it is antibody antigen interaction. So, the antibodies are used as the immobilized ligand in the isolation and purification of various proteins, including membrane proteins of viral origin. Monoclonal antibodies may be linked to agarose matrices by the say CNBR coupling. Then protein binding to the immobilized antibody is achieved in neutral buffer solutions containing moderate salt concentrations. There could be a lot of different ways to elute it, like use of high salt concentration, use of urea or guanidinium hydrochloride, use of cheotropic agents, lowering the pH, and likewise. So, if you see immunoaffinity chromatography, as you can see on your screen, if you see here, there is an antigen immobilized onto the matrix material, the protein, the antibody, specific antibody will bind to it, and then antibody of different specificity could be brought in, and then they could be eluted, or by pH or other changes it could be eluted. So, that is immunoaffinity chromatography is another important form of affinity chromatography. Then there could be metal chelate chromatography. In this technique, an immobilized metal ion, which could be copper, zinc, or mercury, or cadmium, and so on, or transition metals, is used to bind proteins selectively. Binding involves a reaction with the imidazole group of histidine residues, or say cysteine residues, or indole groups of tryptophan. The immobilization of protein involves formation of a coordinate bond that allows protein attachment and retention during the elution or non-binding contaminating material. The elution can be achieved again by similar methods like lowering the pH, using some complexing agents such as EDT, etc. Nickel column is quite widely used to purify recombinant proteins having the histidine tag or polyhistidine tag. Zinc columns could be utilized for isolation of say human interferon. There are other things like dye ligand chromatography, where certain dyes which binds with certain molecules. The exact mechanism is not known, it is not specific, but they could be very good way to purify the certain proteins, like say DNA binding proteins and other things on Sebacaron blue. That is one method of achieving purification. There also you can have elution through salt gradient or affinity elution could be done, which is very important. These are cheap. There are very good methods of purification and very specific. Then there could be covalent chromatography. In covalent chromatography technique, it could be used to separate say thiol containing proteins by exploiting their interaction with an immobilized ligand containing a disulfide group. Now, the most commonly used ligand is disulfide 2 pyridyl group. On reaction with the thiol containing protein, pyridyl 2 thione is released, and the process can be monitored spectrophotometrically at 343 nanometer, thereby allowing the adsorption of the protein to be followed. When the protein is attached covalently to the matrix, then non-thiol containing proteins are eluted and unreactive thiopyridyl groups is removed by use of 4 millimolar diethioethylene or DTT we can say, or mercaptoethanol could be utilized. Protein can then be released by displacement with a thiol containing compound, which could be DTT or say reduced glutathione or cysteines. So, this could be utilized in this way. Here this particular figure shows that particular thing, that you have a immobilized 2' pyridyl ligand, protein binds in here, releases the thione form, and then with another group it could be eluted. It is a very good technique for purification of lot of different SH containing compounds. Apart from the above techniques, there are a lot of different matrix ligand systems could be developed for purifications. Like for example, protein A agarose could be utilized. It is derived from the cell wall of the bacterium Staphylococcus aureus. It has a high affinity for the Fc region of the human immunoglobulin G. There could be polynucleotide and lysine agarose could be utilized, where nucleic acid binding proteins can be purified. There could be boronate polyacrylamide, which has high affinity for binding low molecular weight compounds with cis thiol groups, like say ribonucleotides, sugars, or other many coenzymes, and it could be utilized for purification. Heparin agarose system could be developed, which prevents blood clotting and used to purify bone collagenase, hepatitis B surface antigens, plasma antithrombin 3, and several other like say androgen receptors and other molecules here. So, there could be a lot of different combination. There is one acreflavin agarose. It is intercalates reversibly between the base pairs of DNA and also binds weakly to the phosphorylated heterocycles, for example, nucleotides. So, the binding is electrostatic interaction between the positive charge on the acridine ring and negatively charged phosphate group of nucleotide. Then it could be used to separate nucleotides, oligonucleotides, cyclic AMP, etc. So, there as you see, there are a whole lot of different kinds of combinations or different types of affinity chromatographic methods could be developed. So, what we have seen is affinity chromatography can be used for a lot of different applications, for like say purify and concentrate a substance from a mixture, and depending on the specificity, reduce the amount of substance in a mixture, that is then you can discern what biological compounds bond to a particular substance, that could be also determined. Then you can purify and concentrate certain enzyme solutions and other kinds of analytes. So, affinity chromatography with different kinds of combinations, different kinds of affinity chromatographic methods could be a very useful technique and highly selective, high capacity, one step purification technique which could be utilized. So, this completes the section on affinity chromatography system. The one technique which is left to be discussed, and we are going to discuss in the next lecture, that is gas liquid chromatography technique, which is a very useful technique for certain substances which can be volatilized, and the gas liquid chromatography has been used widely earlier by chemists, biochemists, and a lot of different applications. HPLC has kind of replaced it, but not completely. So, we are going to discuss in the next lecture about the gas liquid chromatography. Thank you.